So get this, we're going deep today, like really deep, into a paper that's causing a stir, you know. Especially for those of you out there wrestling with distributed AI, especially in wireless networks. We're talking graph neural networks, GNNs, but not just like how to use them, but how to train these things. These powerful AI models, right, in a way that's truly distributed and online.
You got it. Fully distributed.
Fully distributed.
That's the key.
And online.
Online.
The paper we're looking at, and it's a mouthful, it's called Fully Distributed Online Training of Graph Neural Networks in Network Systems.
Tackles a huge challenge, a real roadblock, I think, to actually using these GNNs out there in the wild, you know, especially in these environments that are always changing.
Okay, so let's bring it home for our listeners, right? We've got folks deep in the world of wireless networks, signal processing, all that good stuff. Why should they care? Like, why is this paper the one they should be reading? What's the big deal?
Well, I think it's all about flexibility, responsiveness, the kind of things you just can't get with the old way of doing things. Think about it. Most of the time now, training a GNN, it means you're sending all this data to one central server.
Right, so it's all centralized.
Exactly. Yeah. Centralized.
What we know.
Which we know is slow, creates bottlenecks, and it's just, I mean, forget about it if your network's changing all the time. Like, what if you've got a mobile network, you know, or you need to move resources around on the fly? It just doesn't work.
So this paper is saying, hey, ditch the central server.
Right.
Let's make every node in the network part of the training process.
Exactly.
Big shift.
Huge shift. But it's not just about, you know, decentralization just for the sake of it. This paper gives you a way to do it that's actually efficient, which, come on, we all know how important that is when you're talking about bandwidth.
Right.
Limited bandwidth. And it's online, so the learning's happening as the network's running. You don't have this model that's static, that's already outdated the moment you try to use it.
Okay. Color me intrigued. I am. But before we go full on, like, deep into the guts of how they actually do this, let's level set a little, right? Make sure we're all on the same page. Can you give us, like, the 30,000-foot view of what problem they're even trying to solve here?
Absolutely. Let's imagine you've got your network, right? Any wireless network. And we represent it as a graph.
Okay.
Each device, each node on the graph, it's got features.
The features.
Could be its location, maybe it's the channel conditions, how full its buffer is, you name it, whatever's important. And the GNN, its job is to learn.
To learn.
How to predict some value for each node.
Okay.
That's important, right? Could be like the optimal power allocation or maybe decisions about how to schedule links, the stuff our listeners deal with every day.
So we've got our GNN. It's making these predictions based on how the network's structured, each node's little quirks. So what's so hard about training it in a distributed way? Why is everyone making such a fuss?
Well, it all boils down to it's those dependencies between nodes.
Dependence.
You can't just look at one node in isolation. To get a good prediction, it's GNN. It needs info, right? Not just from its own little world, but from its neighbors, too. Yeah. And this isn't just when it's making predictions. Inference. It's for training, too. When the GNN is learning, when we're doing that backpropagation, each node, it needs to know how its own settings are contributing to the error. But that depends on what its neighbors are doing, too, you see.
It's like a group project, right? Where everyone's grade is riding on everyone else, but you can't actually see the whole picture at once.
Perfect analogy.
Right. So what about, I mean, people have been working on this distributed learning stuff for a while now. What about, like, federated learning? Can you use that?
Well, federated learning, it's great if you're worried about privacy because each node, it's only sharing updates with the central server.
Right.
But it doesn't really, it doesn't take into account these dependencies in a GNN, those links between the nodes. It's just not built for that.
Okay. So federated learning's out. What about multi-agent reinforcement learning? Each node is like its own agent, learning its own strategy. Seems like it could fit, right?
It's tempting, but MRL, it usually focuses on, like, each agent learning independently.
Okay.
And that doesn't quite work here. We're talking about a GNN, right? A shared model that everyone's contributing to, the whole network's knowledge. And plus, in MRL, you're usually trying to maximize each agent's own reward, right? Here, we want the whole network to work as well as possible, even if it means some nodes have to make choices that aren't, you know, individually the best.
Gotcha. So federated learning's a no-go. MERL, not quite right. What about just, like, plain old distributed optimization? Can't we just chop up the network and let different servers handle the training?
People have tried that, but it's not truly distributed, right? The way this paper is talking about, you still end up with these central servers, bottlenecks, plus usual distributed optimization. It assumes each node can, like, figure out its contribution to the error on its own, independent, which, again, it just doesn't work with GNNs because of these dependencies.
Right.
You can't escape them.
Right. All right, so this paper's coming in swinging, saying, hey, we solved this really tough problem.
Yeah.
So how do they actually do it? What's their secret sauce?
Well, they get clever. They start by reframing the whole training objective.
Yeah.
They put it into this distributed optimization framework.
Okay.
Reframing.
Think of it like this. You've got this giant loss function. Right.
Measures the error.
Exactly. Measures how wrong we are across the whole network. They break it up. They create these local loss functions.
So each node gets its own little piece of the error puzzle.
Precisely. And here's the kicker. They actually prove it mathematically.
Oh, wow.
That if each node minimizes its own little loss function, and they do a bit of coordinating with their neighbors, you're essentially minimizing the big one too, that global loss function.
Hold on, wait. How do they handle, like, you know, we keep coming back to this.
I know. How do they handle those dependencies? Like during the training process itself, that's the part I'm still not quite, it's still fuzzy.
That's where the real magic happens. This is what makes the paper shine. They come up with this thing, they call it local backpropagation.
Local backpropagation.
It's like regular backpropagation.
Where the error signal goes backwards.
You got it. Through all the layers.
Layers of the network.
Updating all the parameters. But, big but here, they add in these extra terms, right? When they're calculating the gradient. And those terms account for what the neighbors are doing.
So it's not just like, hey, how bad was my prediction? It's like, how much did my neighbor's predictions, which are based on what I'm doing, mess things up?
You got it. Exactly. It's a much smarter way of figuring out who's responsible, right? For the learning process. Each node figuring out its own role. And this is what lets them actually do distributed training. For GNNs. For real.
It's mathematically sound.
Mathematically sound.
Okay. Okay. Starting to click a little bit, but I have a feeling there's more, right? More cleverness.
Oh, yeah.
They didn't just stop there to make this work. Like in the real world.
Oh, there's a lot more.
Okay.
And that's what we're gonna get into.
Okay, good.
Next, we'll unpack all the tricks they use to make this communication efficient and online.
All right, listeners, I don't know about you, but I'm hooked. We're about to get into the good stuff. The real meat of this paper. How do they make distributed GNN training a reality? Stick with us. Okay, so we're back in the thick of it. Fully distributed online GNN training.
Back at it.
That's right. Last time, we got to set the table, right?
Yeah.
Why this research is such a big deal, especially for you folks out there grappling with these dynamic networks.
Right.
And we got to taste a little sneak peek of how they break this whole complex training process down.
We did. We talked about how they use these local loss functions and that really cool local backpropagation method.
Yeah, to handle all those links between nodes.
Most pesky dependencies.
It's pesky, yeah, but we left everyone hanging, right?
A little bit of a cliffhanger.
A little bit.
Yeah.
How do they actually make this training process like efficient enough,
Yeah.
you know, to work in real time?
Yeah.
Especially, come on, wireless networks. Bandwidth is precious.
Right. Scarce resource.
Scarce. How do they do it?
Well, this is where they get really clever with what they call communication efficiency techniques.
Okay. All right. I like it already.
They've got some tricks, some really neat tricks to cut down on the amount of data that has to go back and forth between these nodes.
Okay, lay it on me. What are we talking? How do they keep that overhead low?
One of the coolest things, I think, is this idea of message piggybacking.
Message piggybacking.
They're basically being sneaky, right? They're taking advantage of the communication that's already happening.
Oh, smart.
During training. Think about it. When you're doing that forward pass,
Uh-huh.
a node, it has to send its features to its neighbors, right?
Right, so they can make their predictions.
Exactly. And then in the backward pass, it needs to get those gradients from its neighbors, right?
Right, to update.
Yeah.
So you're constantly sending stuff back and forth.
Right.
Well, instead of having separate messages for the features and the gradients, they cram them together.
They combine them.
One message. Boom.
Oh, that's smart.
Like imagine sending a postcard with a message on both sides instead of two separate postcards.
I got it.
Cuts down, right, on the number of messages, which is, I mean, crucial, right?
It's fine.
Especially when bandwidth is limited.
Big time.
Yeah.
Okay, message piggybacking. Check. What else? What other tricks they got?
Another one, they rearrange that that mini batch update process
Mini batch.
so that they don't have to, so that the nodes don't have to sync up their parameters as often.
Okay, explain that one. I'm not sure I follow.
Sure. So remember, like typical mini batch gradient descent.
Yeah.
You process a batch of examples. You get the average gradient, and then you update.
Right, right. Little steps.
Yeah.
Little steps, then a big adjustment.
Exactly. But when you're doing this in a distributed way, if every node has to talk to its neighbors after every single example.
Yeah, that's going to be a lot of chatter.
It's a lot of chatter, right?
Slow things down.
It's slow, it's inefficient, so what they do is they let each node accumulate those gradients
Oh, interesting.
over the whole mini batch,
Sure.
and then they communicate.
So it's like having a bunch of hikers, right?
I love that analogy.
And instead of them like constantly stopping, checking in, hey, are we still on the right path?
Right.
They just kind of spread out a bit,
Right, exactly.
cover more ground, and then regroup.
Exactly.
Smart.
So the communication happens less often, which saves that precious bandwidth, especially if you've got a really big network.
Okay, starting to see how they're making this this whole distributed training thing like actually work.
Yeah.
But they also say it's online, right?
Right.
Meaning it can like adapt
Adapt.
as the network changes.
In real time.
Real time. So how does that work? How do they do that?
Well, this is another key part. Instead of training the GNN on some like static data set and then deploying it,
Right.
they're training it continuously
So it's learning as it goes.
as the network's operating.
Oh, that's cool.
As new data comes in, each node is updating its local model, right?
Yeah.
Based on what it sees and what its neighbors are telling it.
So it can keep up,
Yeah,
even if the network changes.
exactly. Like a topology changes, maybe the traffic patterns shift, whatever. It can adapt.
Powerful stuff. It's like it never gets stale.
It's always up to date.
Always up to date.
Always making those hopefully accurate predictions. And I think that's one of the things that really sets it apart.
From the old way.
From centralized training, it can't do that.
Okay, I got to say, I'm impressed. They put a lot of thought into this.
They did.
A lot of cleverness,
Yeah.
but, all this fancy footwork.
Yeah.
It doesn't mean anything if it doesn't work in the real world. Did they test this out?
Well, absolutely. And that's what we're going to get into.
Okay.
Next. All the simulations they ran to really show, to demonstrate how well this works.
Yeah.
In different scenarios. It's pretty exciting stuff.
All right, listeners, hold on tight. We're about to see if this revolutionary approach to GNN training, it lives up to the hype. Okay, so here we are, the moment of truth.
The grand finale.
Right. We've talked about the why, the how, all the clever bits that make this approach to GNN training so exciting.
Yeah. All the promises.
All the promises, but did it actually work?
It did. They really put it through the ringer. They ran all these simulations, really showed off what it can do. And then they picked problems, tasks that our listeners would care about, real world stuff.
Okay, hit me with the highlights then. What kind of results did they get? Did it actually live up to the hype?
Oh, it did. First up, they tackled this classic problem. It's called supervised learning for node regression.
Okay, node regression.
So imagine you've got your network, right, your graph, and you want to predict some value for each node, some continuous value, like maybe how much power a transmitter should be using.
Okay, so we're making predictions based on how the network's connected and what each node's like, its individual characteristics.
Exactly. They used a synthetic data set, but the whole setup, it reflects real problems in wireless communication. What's cool is they showed that their distributed methods, they could get results that were just as good as centralized training.
Wow. No central server.
No central server.
But the same accuracy?
No.
I like it. What about other types of learning? Did they just stick with supervised learning?
No, they didn't. They actually tested it on unsupervised learning too, for power allocation.
Power allocation.
Yeah, using a neural network that was it was inspired by this algorithm everyone knows, WMMSE. So they're trying to, squeeze as much throughput out of the network as possible.
Right. Figure out how much power each device should be using.
Exactly. So it's not just predicting, right? It's about actually controlling how the network behaves.
In a distributed way.
And the results, they were, really good. Not only did they beat that baseline WMMSE algorithm.
Oh, wow.
But they got pretty much the same performance as if you'd done centralized training.
Okay. I'm seeing a pattern here. This is getting really interesting.
Right. It works.
It works. But come on, I know they didn't stop there.
Of course not.
They pushed it further.
They had to see how far they could take it. So they applied it to this much harder problem, reinforcement learning, specifically distributed link scheduling.
Ooh, link scheduling. Now that's a tough one. That's like figuring out which links in the network should be active
Right.
at any given time, taking into account like all these constraints, interference, headache.
Big time.
Classic problem. And it's hard enough, even when you're not trying to do it in a distributed way.
So how did their fancy distributed GNN training do in this crazy environment?
Well, it's important to point out that here they kind of they did a bit of a hybrid approach.
Okay,
So
hybrid.
the actor network, the one actually making the link scheduling decisions, that was trained fully distributed, but the critic network, the one that's kind of evaluating how good things are,
Yeah.
that was trained centrally.
Okay, so they're blending it a little bit, centralized and distributed, which I mean, I guess it makes sense for a problem this complex.
Exactly. But even with that hybrid approach, they still managed to beat the baseline algorithm. They didn't quite match the performance of, fully centralized training. But it really showed that the method can handle these tough real-world problems.
This is amazing research, truly groundbreaking stuff. But I know our listeners, they're not just interested in the technical, the achievements. They want to know what it means for them. What are the takeaways? Like, what does this mean for the future of wireless communication, networking, all that?
Well, I think it opens up a whole new set of possibilities. It shows that we can break free from these limitations of centralized training. We can embrace this more flexible, more adaptable future for AI in networks.
So we're talking like faster development of these GNNs.
Yeah.
AI that can actually respond to what's happening in the network, in real time.
Yeah.
And maybe fewer bottlenecks,
Yeah.
fewer points of failure.
Exactly. Imagine self-organizing networks, resource allocation that, it changes as the demand changes in real time, and control systems that are truly distributed, more resilient.
This could change like everything. How we design mobile networks, the Internet of Things, everything.
I think so. And it's not just the applications, right? It's the foundation, the theory, the algorithms, the proof that it can be done. It's all there.
So this is a call to action then for researchers
Yeah,
to take this and run with it.
absolutely. There's still a lot to explore, of course, how to adapt this to other types of GNNs, even more complex problems, how to actually implement this in the real world. But they've laid the groundwork for an amazing future for AI and wireless communication.
This has been incredible. Thank you for walking us through this cutting edge research and helping us understand why it matters.
My pleasure.
And to our listeners, don't just take our word for it. Go check out the paper yourselves. Think about how these ideas might spark something new in your own work. Who knows? Maybe you'll be the one to take this to the next level.
I hope so.
That's all for today's deep dive. Thanks for joining us.